Moving to problem 10.7, we have a motor, 3-phase, 100 horsepower, and it has a 3450 RPM. So these are the nameplate values that we have stamped on the nameplate. So the first question we want to look at is what will be the full load torque of this motor. So if we run the motor at full load, what torque will be produced by a 100 horsepower motor with a 3450 rotational speed. So this is important. We have a 3-phase motor. So if we would turn to the speed torque curve in our chapter 10, this table here, this will give us the torque per speed comparison or relationships. Okay, and if we're looking at along the bottom, our percent full load torque, along the y-axis, percent synchronous speed. Okay, so there's relationships here, and pulling relationships from this chart, we can find our full load torque, our locked rotor torque, and our breakdown torque. Okay, if we remember, full load torque is just 100% of our torque, right? Full load is what it wants to run at, 100% full load torque. Okay, locked rotor torque is then full load torque times 210%. Okay, and breakdown torque is full load torque times 270%. Okay, so those are the relationships. Full load torque is just 100%. Right? It's what it is itself, 100% of itself. Locked rotor is 210% of full load torque. Breakdown torque is 270% of full load torque. So those are relationships based off of that table speed torque curve for a 3-phase motor. Okay, they do not apply for single phase motors. Also, since we have horsepower and speed, we can use our equation horsepower equals our speed and our torques. So rearranging that equation, we would solve full load torque equals 33,000 times our horsepower divided by our 2 pi times our speed. Okay, so just horsepower of the motor, rotational speed of the motor, the nameplate information. Okay, all the nameplate information has to do with full load torque. It's all the nameplate values, the ratings at full load torque. So putting these values into this equation, pi times 3450, we have a result of 152 foot-pounds of torque at full load. So what that means is this motor, a 3-phase motor, 100 horsepower, running at this speed, will produce 152 foot-pounds of torque when it's at 100% loaded. So we put 100% of our load on, or we can get a load that is that requires 152 foot-pounds to drive, and that motor will be running right at the 100% rating it was designed for. Now, locked rotor torque, 210% of full load torque. So we have our full load torque times 2.1. Gives us our 319.2 foot-pounds. It would take 319.2 foot-pounds of torque to lock that rotor up and keep that rotor from spinning. Another way to look at that is it would take at least 319.2 foot-pounds to start that motor spinning. Okay, if we had a load on it. Okay, we need a motor to be able to produce that much torque to start spinning. So we have a load that's 300 foot-pounds. Guess what? Our motor can drive that because it's going to produce 319 foot-pounds to get that spinning. The breakdown torque, of course, is our 2.7, 270%. And that's our 410.4 foot-pounds. So when we're looking at motors, and we say, okay, this motor is 100 horsepower, this is the torque it's going to produce when it's fully loaded. It will not drive a load that's beyond 319.2 foot-pounds of torque. It will lock up at that point and stop spinning. Okay? So if our load is beyond that, it's going to lock up. And then our breakdown torque is where we start breaking down. So if we look at these along here, this is our 100%, our 152. Over here is our 410 breakdown torque. And then all the way down here, our locked rotor, or our zero speed, is our 319 foot-pounds. That is 210% full load torque. Okay, so the next question is, I have a situation where I have a 4-pole motor, split phase motor, and the locked rotor torque is 45.7 foot-pounds, meaning there's a chance that when the load is just sitting there, not moving, it's going to require 45.7 foot-pounds to start that load moving. So what size motor do I need to start this load? I need something just above this, right? So what are we going to do? We want to find our full load torque first, and then we can go to figure out what our horsepower is for the full load. Right now we have a locked rotor torque. So to find our full load torque, the relationship here is our full load torque is actually, and this is actually 10.10, so that's my mistake. Locked rotor torque is 150% of full load torque for a split phase motor. So if we look at the split phase motor, typical split phase torque speed, the locked rotor is 150%, so that's 110, 20, 30, 40, 50. Okay, so that's how I'm getting that 150% split phase motor. So looking at that, we can look at locked rotor here, 45.7 foot-pounds divided by our 1.5 gives us our 30.5 foot-pounds. That's our full load torque. We can take this full load torque and put it into our horsepower equation because we're trying to find what's the horsepower. Horsepower is 2 pi times torque times rotational speed divided by 33,000. Okay, so we just fill in the equation here. 30.5 foot-pounds. Our speed, now our speed, we weren't given it directly, but we can look at table 10.1 to find our speed at a 4-pole motor. Okay, and that's going to be 1725. So we can look at table 10.1 to find that. You could also calculate it, but at this point we can just grab it from the table. And And so we're going to have a resulting horsepower of 10.2 HP. Now, if we're at 10.2 HP, we're just at that point of just producing that much. Yes, are we going to get over it? Maybe, maybe not. We would really want to upsize that to the motor next higher motor. If I get a 10 horse motor, I probably won't start that load. I go to the next size up. The next common size most often is a 10 or 15 horsepower. Okay. So if you look at Grainger and you look at the motors, they're going to go 10, 15, 20, 25 kind of thing. Below 10, they're going to be 7, 7.5, a little more graduations below 10. But above 10, it's larger horsepower in between. So that's how we would find the horsepower of the motor we would need to start this load. Okay, and then we would just pick the one that's the next largest. Okay, so we can look at full load torque relationships, locked rotor, breakdown torque relationships. These are all based on three-phase. If we look at the single phase, they all have their own unique relationships. Okay, so we look at those torque curves in the chapter. Okay.